Welcome to this presentation. The name of the presentation is Electrochemical Treatment for Targeted Recovery of Rare Earth Elements and Yttrium from Acid Mine Drainage. My name is Denise Villa-Gomez and I work at the School of Civil Engineering at the University of Queensland. This work is a collaboration between a company and different institutes within the University of Queensland. Acid mine drainage is a challenge, and it's a challenge not only for current mining operations worldwide, but also for past operations. And it affects ecosystems and communities when it's not adequately managed. And in Queensland, we have around 15,000 legacy mines and 300 classified as mega, large, or medium size. Treatment costs are significant, but even more, sometimes sludge management after treatment is a problem. Therefore, a circular economy approach to acid mine drainage, where concomitant resource recovery is highly appealing to offset the high treatment cost. Targets for recovery for acid mine drainage include metals and metalloids, sulfur products like sulfuric acid, for example, or elemental sulfur, electrical energy, construction materials like gypsum, agricultural soil conditioners, or adsorbents. A further product of special interest are higher value rare earth elements and yttrium. These are required for a clean energy generation, rechargeable batteries, photovoltaic cells, fiber optics, and lasers, and their demand is expected to grow in the near future. There are already anticipated issues with the accelerated growth of rare consumption due to the unsustainable mining, monopolistic supply conditions, and potential geopolitical conflicts. These problems could, however, be alleviated by substitution, security of supply policies, and finding alternative rare sources, such as recovery from AMD treatment. This work demonstrates a novel approach to tackle acid mine drainage, whereby stage electrochemical neutralization is employed to treat acid mine drainage and concomitantly recover metals as precipitates. This approach was guided by physicochemical modeling and tested on real acid mine drainage from two different legacy mine sites in Australia, and compare against conventional chemical dose and base techniques using hydrated lime and sodium hydroxide. The electrochemical produced less voluminous and more easily settable sludge than lime. Moreover, the stage treatment approach demonstrated the potential to produce metal-rich powder solids with a targeted composition, including rare earth elements and yttrium, which are called Ray. Ray were recovered in concentrations up to 0.1% of the total solids composition, illustrating a new avenue for acid mine drainage remediation coupled with the recovery of critical metals. This figure shows that the electrochemical system removes iron, aluminum, magnesium, and sulfate while levels of sodium and calcium remain constant. The modeling results showed some discrepancies with experimental data that could be due to inaccurate chemical databases and the complex solutions with high ion strength requiring a model accounting for more complex activity correlations. Lime addition displays similar removal efficacy compared to the electrochemical treatment. However, towards the high end of the pH range, calcium concentrations in the liquid phase increase. For both sites, all three treatment options that we compare remove nearly all listed contaminants to meet the guidelines, the Australian guidelines for water discharge to the environment, except for sulfate and manganese, and with lime treatment for aluminum. For site 2, the lime treatment removed 20 to 26% more sulfate compared to electrochemical treatment. For site 1, electrochemical reactor 3 removed the most sulfate by approximately 14 to 25% compared to lime. In both cases, Sodium hydroxide chemical treatment did not considerably diminish the sulfate concentration. Lime and electrochemical treatment were similar overall. However, lime treatment had two exceptions in meeting the discharge guidelines. Sulfate levels from all the experiments did not meet discharge guidelines. The following figures show the variation in sludge composition at different pH stages. These graphs clearly illustrate the possibility of producing solid products with targeted composition, dependent on the pH. The variation in bar color in this figure highlights the precipitation of iron, aluminum, zinc, magnesium, and manganese with increasing pH stages. What is very interesting to observe is that maximum concentrations of rare earths and yttrium occur between the specific pH of between 5 and 7 and are consistent between the two types of acid mine drainage. In the dry solids, metals recovered during the chemical experiments were found in lower concentrations compared to metals in the electrochemical experiments, indicating that an electricity-driven process can increase the concentration of metals. More important, in all cases, electrochemically generated solids had a higher percentage in composition of rare earths and yttrium compared to chemical generated solids. Up to date, a pilot plant has been constructed. It consists of 18 cells set up as 2 rows of cells in parallel, with each row containing 9 cells in series. Within the cells, the fluid rose and is treated as shown in the following diagram. You can see that the acid mine drainage is pumped through tiny channels into the cathode side of the cell. Then an electric current is applied to drive anions in the acid mine drainage across the anion exchange membrane to the anode side of the cell. And this process is continuous. Unlike electrodialysis, for example, the reactor contains only anion exchange membranes, meaning that it processes and diverts anions from the fluid. The anions removed from acid mine drainage consist mainly of sulfate ions, but can include also chloride and fluoride ions. As the sulfates concentrate on the anode side of the cell, they form a dilute sulfuric acid. They report to an analyte tank. The fluids can be recirculated through the cells until the desired pH is achieved. An advantage of the process is that the pH can be controlled much more precisely than by adding lime. As the process continues, the pH rises in the remaining fluid on the cathode side of the cell. As the pH rises, various metals precipitate from the solution as a fine paste. Generally, the metals precipitate as metal hydroxides.
Okay, so what we have here is the electrochemical cells. So we've got 18 cells, 9 in series, and then that's parallel with another 9 in series. The acid mine drainage is pumped through these cells and it's treated. In the middle, you have of the cell, you have an anion on one side and an anode on one side and a cathode on the other, and they're separated in half by this anion exchange membrane. There's 18 of these because there's 18 cells. The anion exchange membrane or AEM, when you apply electricity, preferentially allows anions to pass through. The main one being sulfate, SO42 minus. Therefore, as we pump the water through, on the cathode side, it is treated by passing electric current, which removes the sulfates, and then that effectively raises the pH of the water on the cathode side. This then precipitates metals out selectively or sequentially as the pH rises, and different metals will precipitate at different pHs, right up from aluminium around 4 to magnesium around 10, or a little over 10. So what we have here is the control box with the PLCs and the controllers to measure the rate of flow and control the rate of flow and measure the pH of the resulting liquid. We also have data loggers in there to capture the data for analysis.
The pilot plant processes around 200 liters per hour, generally at an electricity cost of about 1 kilowatt hour per hour, including pumping costs. The processing rate varies depending on factors such as the ionic strength of the fluid, the amperage and voltage, and process flow rate. The electrochemical approach produces less voluminous and more easily settable metal precipitate sludge than the addition of lime or caustic soda to neutralize acid mine drainage. The stage treatment approach demonstrates the potential to produce metal-rich precipitates with a targeted composition, including rare earth elements and yttrium. These metal-rich precipitates are in the form of metal hydroxides, with different metal precipitated at different pH values. pH control, therefore, allows for the separation of metals from each other on a more targeted extraction way. The system has been tested in several number of acid mine drainage sources, from open and closed mines in Queensland. It was conducted mass balances to determine the characteristics of the outflows from the process. And well, several tests have been conducted, and we have came up with some important observations. So one of the observations is that it is possible to raise the pH of the AMD from 2.5 up to 12, or even a bit more. At a pH of 12, all metals could be expected to have precipitated from the AMD, noting that some metals such as aluminum may go back into the solution. We were able to precipitate almost all of the metals in the AMD. Elements removed almost entirely, including aluminum, cadmium, chromium, cobalt, copper, iron, lead, manganese, nickel, and zinc. Magnesium is generally removed if the pH is taken above 10.5. It is difficult in multi-cell arrangements to determine the limiting current density. The metal precipitates settle generally as metal hydroxides, occupy little volume, entrap little water, and settle quickly. The process energy costs vary with the ionic strength of the water and compare favorably with the operating costs of the process, such as lime dosing. Other future areas of work around the electrochemical reactor include optimizing the choice of membrane amongst selectivity, back diffusion, mechanical strength, fouling potential, and cost. Optimizing the choice of spacer in the cell among creating a shape that generates turbulence, energy efficiency, and cost. And managing back diffusion once the anolyte tank concentration of sulfate becomes very high. There is room for improvement. One of the key challenges on this system is the fact that the sulfate hasn't been able to be in decrease to optimal levels. So one of the proposed alternatives that we have is the implementation of a bioreactor that transforms the sulfate-rich stream to sulfite. With this sulfite, we actually can also precipitate some of these metals, and we can also use it for sulfur recovery as well. This is an interesting approach because it can allow the system to have a complete full treatment, can offer a full treatment of acid mine drainage. Another interesting future work that is being proposed is the use of a leaching reactor. This is because although all metals are precipitated and are concentrated, which is very important and very interesting from a point of view of recovery of critical elements such as rare earth elements and yttrium, we need to also achieve some level of selectivity. And we can achieve this selectivity by doing some leaching of the sludge, of the obtained sludge. This leachate can be obtained through the use of the sulfuric acid that is being produced in the electrochemical system. But other ways, other alternatives of leaching are also being proposed that can also involve biological bioleaching that can improve the selectivity of this for the recovery of these elements. Thank you all for listening to this presentation, and also to the conference organizers for this opportunity. We hope to see each other soon, face to face, and to keep sharing and discussing these interesting topics, and to share new ideas for treatment and for enhancing the circular economy on acid mine drainage treatment.